Welcome everyone. We are here today to discuss how Bohr's model of the hydrogen atom affects current knowledge of quantum physics. We will be exploring the three postulates of the model, and examining the importance of the angular momentum of the revolving electrons. Let's get started. Niels Bohr put forward a model of the hydrogen atom in 1924 which accounted for spectroscopic data then prevailing. According to Bohr, electrons revolved around the nucleus in established, separate orbits. The energy of the electrons was quantized, thus they could only subsist in particular energy states. The energy of the electron depended on the principal quantum number n and augmented with higher values of n. Bohr's model of the hydrogen atom combines classical and quantum concepts into three postulates. The first postulate states that an electron in an atom can revolve in certain and stable orbits without the emission of radiant energy, also known as stationary orbits. Electrons in the Bohr model of the hydrogen atom exist in a series of orbits, with the quantum number n determining their path. To fulfill the angular momentum of the electron in a given orbit, it must be an integer multiple of Planck's constant h divided by 2 pi. The quantum number n can be defined as the principal quantum number. This model gives us an improved insight into the behavior of electrons and the structure of atoms. An electron's transition from one state to another has the potential to release photons. Examining the pattern of the emitted photons gives us insight into the energy levels between which the electron is transitioning, thus enabling us to comprehend the fundamental characteristics of atoms more thoroughly. The atom's power is truly impressive. Electron movement around a nucleus is determined by electrostatic attraction, creating a centripetal drive that is essential to the atom's structure. We can evaluate the radius of the orbits using a simple equation. This equation leads us to a clear conclusion about atoms, their immense complexity and power. This equation enables us to determine the radius of a single electron's orbit around a nucleus, which is known as Bohr's radius. The value of Bohr's radius for the hydrogen atom is 0.53 angstroms. This understanding is important for comprehending the behavior of atoms and molecules in physical reality. Electrons in the fourth orbital travel at a velocity of 23.3 km per second, which can be calculated from equations. This velocity can be used to gain insight into how an atom behaves as a whole. Mathematical equation presented on this slide provides a concise description of the angular frequency of an electron in a hydrogen atom. It states that the angular frequency of an electron in the nth orbital is equal to the angular frequency of the first shell multiplied by the square root of n. This equation is used to further explain how electrons move around the nucleus of an atom. Examining the motion of electrons in an nth orbit, it is possible to generate an electric current, popularly known as in. This concept presents a powerful illustration of how atoms interact and are the basis for every electrical device. All electrical items owe their existence to this fundamental physical phenomenon. Electrons can revolve in certain orbits which don't emit radiation. These orbits are referred to as stationary orbits, elliptical orbits, and geostationary orbits. Additionally, unstable orbits are also possible. The total angular momentum of the revolving electrons is equal to the product of their mass, the radius of their path, and their rotational speed. This angular momentum is an integral multiple of Planck's constant divided by 2 times pi. The options given are either Planck's constant divided by pi or the number of rotations over Planck's constant divided by pi. The correct choice is h, 2 pi. 4 equations have been presented to show relationships between two variables. Inverse proportionality implies that an increase in one variable results in a decrease in the other, while direct proportionality suggests the opposite. In addition, not equal and equal signify that two variables are either different or equal. This illustration allows us to comprehend the connections between distinctive variables. Ionization energy is the energy needed to take out an electron from an atom. Excitation energy is the energy necessary for an electron to transform from its ground state to a higher energy level. Binding energy is the energy which keeps an atom together. This slide concentrates on these three types of energy found in atoms. Ionization energy of an atom is the amount of energy required to remove an electron from its orbit. Its potential energy is dependent on the electron's distance from the nucleus. Thus, ionization energy is a significant factor in determining the stability of an atom and its capability to create chemical bonds, and is thus a crucial concept to be understood when engaging in chemical research. The potential difference an electron needs to acquire an energy equal to its ionization energy is the ionization potential of a hydrogen atom. It is an important concept in atomic structure, as it helps us learn how atoms interact with each other. Knowing the ionization potential of a hydrogen atom is essential for gaining a deeper understanding of the fundamentals of chemistry. Atoms can gain energy from an external source and move to a higher energy level, a phenomenon known as excitation. The energy needed for this to happen is referred to as the excitation energy, and the potential resulting from this is called the excitation potential. Knowledge of how atoms respond to different energies is crucial to studying chemistry. The structure of an atom is characterized by the number of spectral lines acquired from the transition of electrons from higher to lower orbits, which is a significant factor. Also, the binding energy of an atom or system is determined as the energy released upon combining particles from an extended distance. For instance, when electron and proton are combined from afar, 13.6 electron volts energy is released, constituting the binding energy of the hydrogen atom. Energy is a crucial element in the universe, and this diagram illustrates its behavior at the atomic level. Observe how each nucleus has distinct characteristics, represented by the various energy levels. This representation yields comprehensive information regarding the orbitals of electrons and the energy levels they inhabit. Having knowledge of the interactions between atoms allows us to establish complex chemical structures and construct the environment that surrounds us. The potential of the atom is astonishing. It takes a certain amount of energy to get an atom to an enthusiastic state. For instance, in the case of the hydrogen atom, the energy required to transfer an electron from its ground state to the first elevated state is 10.2 electron volts, while the energy required to move the electron to the second excited state is 12.9 electron volts. When an electron transitions from an excited state back to the ground state, its kinetic energy rises while its potential energy and total energy go down. These small but potent particles give rise to a lot of possibilities. Answer: an atom gains or loses an electron from its electron cloud, resulting in a charged species. This process is called ionization, and the energy required to produce the ionization is referred to as the ionization energy. Therefore, the answer to this multiple-choice question is D. Excitation energy, which is unique to each atomic state, plays an important role in our scientific understanding of the structure of atoms. This energy is necessary in order to excite an electron in an atom, and furthering our knowledge of the structure and behavior of atoms depends on our comprehension of this concept. Atom is the pivotal element of the slide and a powerful originator of energy. Potential energy, stimulation energy, ionization energy and binding energy are all methods of energy obtained from atoms. This energy can be employed for a variety of purpose, ranging from running our homes, vehicles, computers and smartphones. Knowledge of the science underlying atoms can assist us in exploiting and using this energy efficiently. Bohr's theory of the atom, proposed in 1913, brought a revolution to atomic physics. Although groundbreaking, the theory was not able to explain the transition of electrons between orbits, which was later resolved by quantum mechanics in the 1920s. Despite its limitations, Bohr's theory was a major step in understanding the structure and behavior of atoms. When an electron moves from a higher energy level to a lower one, a photon of specific frequency is released. We can calculate the energy of the released radiation using Rydberg's constant, which is equal to 13.6 electron volts. This knowledge can give us a better idea of the special nature of atoms. Atoms typically give off radiation. The frequency of the radiation emitted can be determined by the wave number, the number of waves in a unit length. Wave number can assist us in understanding the radiation emitted by an atom. Bohr's atomic theory was revolutionary for its time, yet it had its limitations. Sommerfeld revealed that orbits were not circular as the theory assumed, but rather, elliptical. It was additionally unable to explain the intensity of spectral lines or the nucleus rotating on its own axis. Though the theory was valid for single electron atoms such as hydrogen, helium, lithium and beryllium, it could not accurately depict the minute structure of spectral lines. Spectral line splitting and the Zeeman and Stark effects are highly valuable in atomic spectroscopy. Sodium's doublets, located at 5,890 angstroms and 5,896 angstroms, offer a reliable identifier of atoms and a deeper understanding of how they interact with their environment. Bohr's atomic model made an important contribution to our comprehension of atoms and their behavior. However, it had some restrictions, such as not being able to elucidate the intensity of spectral lines or take into account elliptical orbits. Moreover, it was only valid for one-electron atoms. When this model is applied to atoms with multiple electrons, it is unable to precisely describe the behavior of those atoms. Niels Bohr proposed a new model of the atom in 1913, but it could not explain many observed phenomena like the Zeeman and Stark effects. These effects are related to the way electrons interact with electromagnetic fields, resulting in splitting of atomic levels. This gave us a more precise understanding of the inner workings of an atom than Bohr's theory could offer.